Go ahead, Balwinder.
Okay, thanks, Luke. Like Luke mentioned, today I'm going to talk about debugging E3SM atmosphere model. And this is a new tool which was inspired by perturbation growth test, which I'm not going to talk about that test in this talk because that is a talk in itself. This work has been done by me with great help from Phil Rash and Hui Wan. And I would also like to mention that this talk is more geared toward new and intermediate E3SM users and developers, and the more seasoned E3SM developers can also be helpful for them as well, because of the tool which I'm going to talk about in this talk. So here's the outline of my talk. So I will talk about classes of model errors, where I will categorize what kind of errors we typically get when we run the model and how easy or difficult they are to debug. And I will also briefly go through the reasons why E3SM-like codes are harder to debug, and some commonly go-to debugging tools which a lot of people use for debugging issues when they get into an issue. And then I will go through the E3SM atmospheric model, which is EAM, inbuilt debugging tool, which is the focus of this talk. And then I will go through the test cases to demonstrate how to use these tools. So this is a typical workflow. Most people might be familiar with this workflow. Like whenever we decide to run a simulation, the first task is we need to find out the simulation configuration. And we do that in the configure step. And configure step is a step where we tell the model that this is the COM set we are going to use. These are the model components we are going to use. And in this step, what model does is it assembles all the codes which it needs to compile. So model like has a lot of codes, but we do not compile all the codes when we run the model. So at configure step, we decide which codes we need to compile, and we do that by mentioning COM set and grid we are going to use. And once we assemble all those codes, we give that codes to the compiler. The compiler compiles those codes for us. And this is achieved by a simple step like simple command like case.build. And after the model is built, then we run the model. And this is also a simple script. We just issue a case.submit command, and the model then runs. And after that, we analyze model output. And this is done by typically using E3SM diagnostic package. And users may have their own tools to analyze the model output. And the first three steps, like configure, compile, and run, they are typically achieved by running a single script, which is run E3SM script. And then the analysis of the model is done by using E3SM diagnostic package. So now we'll go through each step and discuss like what kind of errors do we get and their complexity level. So the first step is configure, and when we run into configure issues, they are typically easy to resolve, although there is a range. There can be issues which are harder to resolve, but typically they are on the easier side. And the one reason for that is like whenever you're getting into configure issues, the model stops right away, and it is very easy to reproduce those errors because it is very quick and you can try different fixes. So that way it is on the easier side. And also these scripts are written by like E3SM folks, and we can contact them if we run into these errors. And typically they are easier to resolve, but there are cases when they can be hard to resolve, especially on new machines, or if there are like environment variables. A new user on a machine also typically get into these errors if the environment is not set correctly. But they are relatively easier to resolve. And then we have these compile time errors. So when after configuration, the models start to compile the codes, and here also we have a range of errors, and they go from simple errors like undefined variable or type mismatch, And the nice thing about compile time errors is like you get the line number, you get the file. So it is pretty easy to go to that particular line in that file and fix those errors. And then there are like errors like circular dependencies, where one code or one module depends upon another module, and there is that interdependence and the code cannot compile. Then you have to break that dependency so that you can compile the code. And the most difficult to resolve errors are like internal compiler errors, when that is where the compiler just give up and it says that there is some error which it can resolve. You have to send the code to the vendor, and again the code is so big, so complex, it is oftentimes not easy to send the code to the vendor. And we resolve those errors typically by changing compiler versions or looking at the flags and maybe looking at your code as well, if you can find something. But their complexity level is a little more than configure issues, I would say. And but it is lower than the runtime errors, because runtime errors can show up anytime, like during your model run. Sometime you run say for 3 months and you get into some error, and then you have to find a fix for that. And there also exists a huge range. They can go from simple errors where you are just like the error is very clear, because because the code itself writes out an error message, and then you can see what has gone wrong. And then there could be segmentation faults, sig terms, which are very cryptic, and sometimes if you do not get a traceback as well, like traceback is where the code tells you which line, at which line the code stopped working. If you do not even get a traceback and you get a seg fault or sig term, they are typically harder to resolve. And then there are memory issues when the code just blows up and you either you do not get an error message, or the error message is very cryptic. And then there are node issues, and the model can run in various ways, so there are threading issues and things like that. So they can be harder to resolve, but still you know that something is wrong because your model crashed. The last kind of errors are wrong answers. These are I would say the hardest to fix and locate and fix, because the model runs fine in these cases. Like it configures, compiles, and runs, and it just runs fine, and you don't see any sign of model crash or anything, any sign of anything going wrong, until you analyze the output. Sometimes it is very easy to locate these errors, because you immediately see that there is something wrong in some of the fields. And sometimes it is harder because the signatures appears only in some fields, not all the fields. And also then you start noticing like there is an impact on other fields, but it is very, very small. And these errors are hard to find and fix, and because sometimes you don't even know that there are these errors until somebody finds that. So today I'm going to talk about these kind of errors, like wrong answers. When you get wrong answers, how to resolve those errors, or how to find what is causing those wrong answers. So I'm going to briefly talk about why E3SM is harder to debug. So the first reason is it's the parallel nature of the code. The code is huge, which is my second point, like the size of the code. And we typically run this code in parallel because we run the model at high resolutions. So the parallel nature of the code make it difficult to code, because and find problems, because the parallel codes are typically harder than the serial codes. And there are various ways we can run the code in parallel, so that also contributes to the issue of finding problems if there exists a problem. And then the second is size of the code. It is huge. And here I found this on web about CESM, and E3SM branched off from CESM. So it may have more lines of the code, but it sits like it sits at 1.2 million lines of code. And so that also makes it harder to debug, because there are so many configurations model can run in. And so that is also a factor. And then there it is a legacy code, so people use different coding styles. So whenever you are debugging a code, you get into different parts of the code, and the coding style is very different, which also makes it um, harder to find problems in the code, or harder to understand the code. And then we have a lot of dependencies, and it typically takes about a day or more to run the code on a new machine. So there are a lot of dependencies which make the code very fragile. And then we have scattered error log files. There are times when it is hard to locate the error. Typically, error appears in e3sm.log file in the run directory. However, there are times when you don't see any error there, but you have to locate the error logs where the error is. And for people who have a lot of experience in E3SM, they know like where to find these errors, and these are in continuous flux, like because Seam is under continuous development, so these keeps on changing a little bit with each version of the model. And like I said, model is configurable in so many ways. So whenever you are developing code, you need to be sure that your code does not break other features of the code. So testing does a great job here. Like we test the code every night, and if it is breaking some other configuration which we care about, then we know immediately. But still, whenever we are developing code, we need to make sure that we are aware of other model configurations. So whenever people run into some issues, these are pretty typical debugging tools they use. The good old print statements are still extremely useful, and I think these are the best for debugging if you know your code. So judicially placed print statements makes it way easier to find issues in your code, and it is extremely fast as well. But you need to know where to put those. And then we have these general purpose debugging tools, and these tools, they don't care about like what kind of code it is. They run for pretty much all kind of codes, and they give you a pretty good overview. And I typically use debugger while developing the code, just to go through the code and see the ranges and the variables and what kind of values they are taking, just to be sure that they are within range and everything makes sense. And these are great tools, and I use them a lot. And then we have open source debuggers like GDB, Valgrind, and they are also extremely useful whenever we get into errors. Like typically for memory errors, people use Valgrind a lot, and they are very useful tools. However, inbuilt debugging tools, which I'm going to talk about in next slides, has an edge over general purpose debugging tools, because we can design inbuilt debugging tools. We can develop these tools in such a way that they are aware of the model data structures, and that is their advantage, that they know the internals of the model, they know the internal data structures of the model. So if you work with E3SM, you know that the output files, like the model history files, the output is in latlon. Latlon grid if we regrid the model output. So we get a latlon output, and if we see that something is wrong in the output, then we know the places in terms of latlon where they are wrong. But it is hard to map that back into model internal data structures, which uses chunks and columns. I will go through that in my next slide. But I just wanted to point out that there is a disconnect between model output and the data structures which are used within the model, and there are good reasons for that. However, it is hard to map them back. There are ways, but it is still hard to map them back. So for example, if you find a problem that there is a temperature or pressure which is wrong at a particular latlon, then we would use this physics debug tools. These are already in the model. They has been there for a long time, but I have seen folks who do not know about these tools, and Phil Rash made me aware of these tools, and these are great, and I use them a lot in my debugging exercises. However, if you do not know what is wrong in the model and which variable is causing the problem, but you know the answers are wrong or where the problem first appeared, then you would use these PERGRO driven debugging tool. So this tools allows you to find which physical process is the culprit, or which physical process and which variable is causing the wrong answers. So first I will talk about the physics debug tools, and then I'll talk about the PERGRO driven debugging tool and the connection between them. So like I mentioned, there is a disconnect between model output and the internal data structures, and the model output is in the lat-lon, and internal data structures are what we call a column and chunk. So chunk is just a collection of columns. So for atmospheric physics just operates on a single column, so independently. So every column is independent of another column, and model physics operate on each column, and this gives us a huge advantage because we can compute everything in parallel. So so when we have columns and we group them together, and we call that a chunk. A chunk is a group of columns, and when we are running it on multiple processors, we assign each processor with multiple chunks. So each processor get multiple chunks, and in that chunks we have columns. And now if we know the lat-lon of a point where there is some issue, like temperature is wrong or pressure values are unexpected, or something like that, if we know the lat-lon, we can simply insert that lat-lon into the name list. So here you see like the name list changes which is required. So you would simply put that lat-lon, if you know that lat-lon, into this phys debug lat and phys debug lon. And once you insert this, you can go into the code and use print statements to print out the offending variable if you know about that variable. So the way it works is like you would insert this I call is equal to phys debug call and give it a chunk. And if that column with that lat-lon exists within this chunk, the I call will be positive. If this chunk does not contain that column which has these lat-lons, the I call will be 0. So if I call is greater than 0, then you can write your variable, print your variable, and see what the values are, and then you can track back using just finding out how this variable is being changed by various equations. And you can use print statements, and you are assured that every print statement will correspond to that lat-lon. And this is very useful because even if you change the PE layout, like the processor layout, and the chunks and columns will be redistributed, in that case, this will stay. This will stay the same. So even if with different PE layouts, you can print the values at the same lat-lon. But then you need to know that lat-lon, and the way to know the lat-lon is using this PERGRO test driven tool. So what this does is it provides you with the physical process which is causing the problem, and also the variable which is causing the problem, and also what is the maximum difference. So for example, if you have two simulation, one is producing the right answers, other is producing the wrong answers. For example, if your restart is broken, or if there is a compiler bug, or these kind of problems, then you have access to the right answers, and you have access to the wrong answers. Then you would put this in the name list, like PERGRO test active is equal to true. This will activate this test. So what this test does is it goes through the time loop of the model. So it will go through each process, invoke each process, and after each process, it will dump out the output of the state variables. So you would know the state of the state variables after each process. And when you compare the two files, one with the right answers, one with the wrong answers, using a script which is provided with this tool, that script will tell you like at which process the simulation started to differ and which variable had the maximum difference and what that difference was, and also at what lat-lon is the maximum difference. So once you have access to the lat-lon, you can simply use fizz debug tools, provide that lat-lon, and start your debugging process. So this is how these two tools are connected, and they can be used to debug various problems. So here is a scenario. For example, if you have a broken restart test, so what that means is like you modified some code and now your restart is broken, and two runs, one, for example, if you run the model for straight 1 year, and then another run you run the model for 6 months, and then you restart and you compare the model history file after a year from both these runs, and they are different. And this is not what we want, because if that is true, then your output or your final answer will depend upon number of restarts you had. So if you have something like that, I would carefully review the new code modifications. If I can't find anything there, then I will see if there is new variables which needs to be in the restart files, and then I would also use the debugger print statement just to review the code and make sure that everything is okay there. And if I can't find anything there, then I would use these tools. And I'm saying that because it is much easier to review your code and find bugs rather than using any other tools. And once you can't find any obvious mistake, then you can use these tools, because these tools will guarantee that you will find the line of the code which is causing the problem. But sometimes it takes a little bit of time because you have to run the simulations again and again. So this is how I would use these tools efficiently, so that I do not need to repeat the simulations, and even if I'm repeating, they are not very costly. So what I would do is I would try to reproduce the problem like any debugging exercise. I will try to reproduce the problem at the coarsest possible resolution, and with the least number of time steps, so that I can get to the problem as fast as I can. Because if it takes longer, that will just increase your debugging time. And I would also switch off compiler optimizations, because even if you add print statements here and there, compiler optimizations does play a role. It changes your code, so switching them off is a very good strategy. And I would also use all compiler debugging options, and that is to get maximum help from the compiler. And compilers are extremely useful, because even if you read through their warnings, and even if you go through the messages which compiler prints out, that gives us a lot of good information about the code. And so I found compilers to be very useful, and their warning messages and else are very useful. And so I generally keep compiler debugging options turned on for these exercises, and switch off compiler optimizations, and reproduce the problem as fast as I can. And after that, I would run the PERGRO test, and this test will isolate the physical process for me, which is causing the problem, or where the answers start to differ. And then I would launch the script which is associated with PERGRO test, and this script will print out everything like the model physical process, and also the lat-lon of the process and the maximum difference. And once I have that information, I can then launch fizz debug tool to isolate the line of the code which is causing that difference. And so that is a whole debugging exercise, and once we know the line, we can find a fix for that. And these are the list of common test cases which we can where we can use this tool to fix these issues. So for example, unexpected non-bit for bit model results, when we expect the model to be bit for bit but the model is not bit for bit, then we can use these tools to track which process, which variable started to differ when. For example, broken model restart, and whenever we perceive the model to be bit for bit, but there are changes which causing non-bit for bit answers, and also non-bit for bit results due to broken threading. We can use this tool to debug that as well. And then if there are wrong answers, we can use this tool as well to find if there are unexpected results or there are bugs in computing environment. So these are some of the common test cases which I have used this tool for debugging. And here's a list of some of the recent debugging exercises. For example, I went through an exercise where there was a bug in Intel 1903 compiler on Compy. Uh, and Pat Worley went through an exercise where he discovered non-bit for bit results due to changes in fizz load balance, and we expect the answers to be bit for bit. And I also found bugs or problems with the radiation diagnostic codes using this tool, and also the MAM code as well. I found issues with the MAM code and fixed those issues using this tool. And I know Hui-Wan and others have used this tool in their SciTech project as well. So so these are some of the recent exercises I went through using these two tools. And and this is the end of the talk. And any questions, I would be glad to answer.